So welcome everybody back. And we are here to hear the last lecture by Ben Howard in his lecture series on arithmetic Siegel for degenerate coefficients and applications to real functions. Ben, all yours.
Okay, thank you. All right. So in this last lecture, we're going to keep the same setup from the previous two. So as before, x prime to x is an étale double cover of curves. Smooth, projective, geometrically connected. Over our finite field K. Okay, so last time I sketched the proof of this Feng-Yun Zhang theorem of this higher derivative arithmetic Siegel formula for the non-degenerate coefficients of the Eisenstein series relating their rth central derivatives to these special cycles on moduli spaces of Shtukas. And now I want to talk about the theorem that I stated in the second lecture after that, which is the next case where you allow some slight degeneracy. So I'm going to call that theorem A. So this is in joint work with Tony Feng and Mikhail Merkchen, which, as long as I live, I will never be able to spell without cheating. Merkchen. Okay, so the statement is this. For rank n Hermitian vector bundle EA on our double cover. So remember the non-degeneracy said that this map, this Hermitian form A, viewed as a map from E to its dual, was injective. Now we're going to assume that when you take the kernel of this map, it's a vector bundle of rank 1. So the Hermitian form. So if you work generically, you get a Hermitian space over the field of rational functions on x prime, and I'm saying that the Hermitian form on that Hermitian space should be degenerate, and it should have a radical of dimension 1. So in that case, the special zero cycle So in this case, we had these sort of naive cycles, and we corrected them in order to get something in the codimension that we wanted. And in this case, where this kernel has rank 1, we have to correct it by intersecting it with one copy of this distinguished codimension R class to end up in the codimension Rn Chow group of the moduli space of UN Shtukas with R legs. Now I have never defined this script L for you, so I'm going to have to do that today in order to sketch the proof of this theorem. The special zero cycle, so what's the conclusion? The conclusion is the same as in the non-degenerate case. This special zero cycle has degree. The central rth derivative of the EA Fourier coefficient of some Eisenstein series EHS on the quasi-split UNN over the field of rational functions of our curve. So this is the same Eisenstein series that I defined, the exact same Eisenstein series that I defined in the last lecture. Okay, so that's theorem A. So as I explained last time, because everything is unramified, the sign in the functional equation of this Eisenstein series is 1. And so the functional equation forces this rth derivative to vanish whenever r is odd. And similarly, this naive special cycle is empty when r is odd. So when r is odd, everything vanishes. Everything is 0. So we're going to assume that r is even. And in the proof of this theorem, we don't prove it directly. We deduce it as a corollary of another theorem, which looks similar but different. So if you have just a Hermitian vector space, but your Hermitian form is degenerate, it has a radical, you can mod out by the radical, and then the quotient space will have a non-degenerate Hermitian form on it. And so you can do the same thing with this vector bundle. So we're going to reformulate theorem A as follows. So from this degenerate EA of rank n, we can construct a non-degenerate E prime A prime of rank n minus 1, where the underlying vector bundle is just you take the Hermitian vector bundle you started with and you mod out by the radical, which is the kernel of A. And then A prime is somehow uniquely determined. It's the unique Hermitian pairing such that the quotient map from E to E prime respects the Hermitian structures. In other words, the Hermitian form A on E descends through the quotient map. Okay, and now here's an exercise. What is this naive special cycle that's determined by the pair EA? Well, we're supposed to take E and we're supposed to map it into some UN Shtuka, which is some chain of self-dual Hermitian vector bundles of rank n. Well, any map from E into some Shtuka factors uniquely through this quotient. And so to give a map from E into this Shtuka is the same as to give a map from E prime into this Shtuka. And what that is telling you is that this special cycle determined by the pair EA is actually dead equal to the special cycle determined by this non-degenerate pair E prime A prime. So the special cycle for a degenerate coefficient is related to the special cycle for a non-degenerate coefficient in this very simple way. There's something similar, but slightly more complicated happening on the Eisenstein series side. So in general, degenerate coefficients of UNN Eisenstein series can be expressed in terms of non-degenerate coefficients of Eisenstein series on a lower rank unitary group. And in our case, where our degenerate coefficient is just very mildly degenerate, this kernel has rank 1, the relation is very simple. So in our case, although it's simple, but it's still complicated enough to be interesting. It's a little bit more subtle than just this very naive relation between the two cycles. So in our case, what it says is that the Eisenstein series of interest, if we take our EA coefficient at S, you get an Eisenstein series coefficient of lower rank, but shifted in the variable S times a Dirichlet function. So L2S eta times E prime, E prime, A prime, S plus a half, where eta is the quadratic character associated under class field theory to our quadratic extension of function fields. And the prime on the E it's not a derivative, it's just bad notation. E prime H S is another Eisenstein series. On U n-1, n-1. And this can't be true, as I've stated it, because the left-hand side has a functional equation in S goes to minus S, and the right-hand side also has a functional equation, but it's not in S goes to minus S. So in order to make this true, you have to symmetrize it. And now it's at least compatible with the functional equation. So in the theorem that we want to prove, we've got this rank n degenerate Hermitian vector bundle. The left-hand side, we can replace it, we can express it in terms of some rank n-1 non-degenerate Hermitian vector bundle, and same for the Eisenstein series. And so if you just replace both sides of the desired equality by the corresponding thing expressed in terms of E prime A prime, and then just rename everything to clear up the notation. So now renaming E prime to E and E prime A prime to EA, theorem A is equivalent to theorem B, which is the thing that all the hard work goes into proving. Theorem B now says that for R even, and EA, a non-degenerate, Hermitian vector bundle on X prime, now of rank n-1, if we take the degree, sorry, up here, right, in this intersection, no, I wrote it, I said it has degree, right, so now the degree of the special cycle intersected with this distinguished thing of codimension R is the arth derivative of this product of a Dirichlet function and the coefficient of another different Eisenstein series shifted away from the center of its functional equation. And now this new Eisenstein series lives on the lower rank group. This is what I want to sketch the proof of. So this is what we really prove. This is what we actually prove. And then that implies theorem A. And now I did all that work in the previous lecture so that when I try to explain the proof of this, I just have to explain sort of what's different and what's the same. So in the previous lecture, this non-degenerate arithmetic Ziegel-Wey, everything somehow came down to analyzing the geometry of this Hitchin vibration. And there's going to be let me point out, everything here is expressed in terms of this vector bundle of rank n minus 1. But these cycles, everything here, we're still working on the moduli space of UN Shtukas. So it's still codimension Rn, Shtukas with R legs on UN. So that n in the Shtukas is not dropping down to n minus 1. That stays the same. Okay. So what is the analog of the Hitchin vibration in this situation? Well, it's kind of exactly the same. So we're going to form a new Hitchin vibration. I'm going to call it the same thing, m over a. The base of the Hitchin vibration is still going to be the moduli space of the things that are parametrizing the two sides of the equality. It's going to be the moduli space of all possible EAs. So non-degenerate things of rank n minus 1. Non-degenerate rank n minus 1 Hermitian vector bundles EA. And the Hitchin space is going to consist of, well, things on the Hitchin base and a self-dual Hermitian vector bundle F of rank n. And then a map from E to F, respecting the Hermitian forms. So the point is that this special cycle associated to EA, we're taking this rank n minus 1 E, but because we're on the moduli space of UN Shtukas, we're trying to map it now into a Shtuka consisting of modifications of rank n self-dual vector bundles. And in the old Hitchin vibration from the previous lecture, the E and the F would have had the same rank. They would have been rank n. And in the old Hitchin vibration, when you look at sort of isometric embeddings between two Hermitian vector bundles of the same rank, there's not that many of them. And so a big part of the argument last time was that in the old Hitchin vibration, we got a map that was generically finite-étale. And that's going to be really far from being true here. Given an A of rank n minus 1, there are just too many ways, lots and lots and lots of ways to map it isometrically to something of rank n. So this is much more complicated than the previous Hitchin vibration that we had. But all the same, the idea is the same. We're going to form the higher direct image of the constant sheaf under the Hitchin vibration. So that's still in the derived category of L-adic sheaves on the Hitchin base. And construct some endomorphism of it, T, something like a Hecke operator. Such that the degree of this intersection is for all points, for all of the points in the indexing set of our coefficients, this is the trace of the Frobenius composed with R copies of T acting on the stalk of the higher direct image at that point of A. So this is how we're going to try and understand the degree of this intersection and then match it up somehow with the analytic side. So if you were at my last lecture, this should look very familiar. It's the same basic idea, except now we've got this extra intersection with L in here. Now, I have never told you what L is, so let me tell you what L is. Recall, L was an intersection of other things. And these other things are tautological bundles on our moduli space of Shtukas, identified with, thought of as divisors modulo rational equivalents. So there is R of them. You view them as elements in the codimension 1 Chow group. You intersect all of them, and you get some distinguished codimension R cycle class. So what are these line bundles? Okay, so I'm going to explain how to attach a k-bar vector space. So to any, so we need to attach R one-dimensional k-bar vector spaces to each point in our moduli space. Okay, so I'm going to tell you the fiber of these tautological bundles at every geometric point. Well, what does a geometric point look like? A geometric point is a UN Shtuka with R legs, which is a gadget that looks like this. It was this sequence of simple modifications of self-dual Hermitian vector bundles. And what did these simple modifications mean? The condition of a simple modification was that these rational maps, the modifications, had a particular form. They came from these honest maps from some other vector bundles. And each one of these diagonal arrows was just making a vector bundle a tiny, tiny bit bigger. Okay? And remember that the definition of a simple modification was that, for example, if I just want to tell you what the first one of these line bundles is, let's focus on the first modification. Well, F0 modulo the image of F0 intersect F1, this is a skyscraper sheaf on X prime at the point of the modification X1. And then if I look at so that's the co-kernel of this arrow. If I look at the co-kernel of the other arrow, F1 mod F0 intersect F1, that's a skyscraper sheaf at the conjugate point. Okay. So let's look at the second point. If I take the stalk of F1 mod F0 intersect F1 at the unique point where the stalk is non-zero, that's a one-dimensional k-bar vector space. Okay, so that means what? To every k-bar point in the moduli space of Shtukas, I have now attached a one-dimensional vector space. This is the fiber of the first tautological bundle at this point. And then the other tautological bundles are defined in the same way. There's one for each one of the modifications. L2 up to LR are constructed similarly. So that at least now I've defined every term appearing in theorem B now. Okay, great. What do we need? Now I want to tell you what this Hecke operator T is. And if you remember last time, this endomorphism, this Hecke operator on the direct image of the constant sheaf under the Hitchin map, it was constructed by some sort of geometric correspondence on the Hitchin space M, this Hecke stack that I defined. So we're going to do the same thing. We want a Hecke stack for our new Hitchin vibration. New Hecke stack. Still called Hecke, like the old Hecke stack. And this is going to be the following moduli space. It's going to parameterize a point EA of rank n-1, non-degenerate, two rank n self-dual Hermitian vector bundles. A modification between them at some point x, and then a map from E into both of them compatible with the modification. A simple modification. Zero to F1. Some x. And E mapping to both. The moduli space of all such things. And so this Hecke stack, by construction, okay, it maps all the way down to the Hitchin base just by remembering EA. And then it has two maps to the Hitchin space M. P0, P1, where this P0 just remembers E to F0, this guy remembers E to F1, and to get all the way down to A, you just remember only E with its Hermitian form. But there's a difference between this Hecke stack for this Hitchin vibration and the picture from last time, which is that in the picture from last time, the arrows P0 and P1 were the source and target of the maps actually had the same dimension. But here the situation is more complicated. This Hecke stack has dimension 1 more than the dimension of M. And so if you want somehow a correspondence on cohomology that preserves degree, you can't just pull back to M and push forward again, because you'll end up in the wrong cohomological degree. So what you do is correct that by putting cupping, when you take a cohomology class on M, you pull it back by P0, and then I'm going to cup it with some distinguished class on the Hecke stack, and then afterwards push it forward by P1. And the point is that I wrote out carefully this definition of these tautological bundles on the moduli space of Shtukas, and you can see that each line bundle just came from one modification. A modification somehow determined a line bundle. Well, this Hecke stack includes a modification as part of this data. So this Hecke stack has its own tautological bundle on it. there's a tautological bundle L on the hecastack. Constructed exactly, constructed in the same way as L1 up to LR. And so you can use that to construct this endomorphism T. So here's what you do. Take its Chern class, first Chern class, C1 of this tautological bundle in the degree 2 cohomology of the hecastack. Okay. This determines an endomorphism of the higher direct image. Why? Because, okay, I mean, I'm not gonna, the construction of the whole endomorphism in the derived category is a bunch of cohomological hoo-ha nonsense, but fiber by fiber, it's something extremely concrete. At each point, EA of the Hitchin base, we can go back to this correspondence diagram and just fiber it over that point. So I can take the hecastack, take its fiber at EA, it maps to the Hitchin fiber at EA, another copy of the Hitchin fiber at EA, and all mapping down to spec K bar. And then I still have these maps P0 and P1. Okay. And then the action of T, fiber by fiber, is, okay, well, if I take the ith higher direct image and take its stalk at EA, that is the ith cohomology of the Hitchin fiber. If I have a cohomology class in this Hitchin fiber, I can pull back by P0. And then I'm going to take its cup product with the Chern class of the tautological bundle on the hecastack to shift the degree up to 2. And now, because this map P1 has relative dimension 1, if I push forward by P1, that shifts the cohomological degree down by 2. And so I end up in the right cohomological degree. And that's what this endomorphism T is on stalks, fiber by fiber. Okay, and I claim with this endomorphism, this relation is true. And the explanation for it is complicated, but it's basically some kind of extended form of the Grothendieck-Lifshitz trace formula. Now, what was the next step last time when we were looking at non-degenerate coefficients? So the next step was to take this sheaf on the Hitchin base, this higher direct image of the constant sheaf, and understand what it looks like by, we decomposed it as a direct sum of sheaves, and each summand was stable under this endomorphism T, and T acted in a really simple way on each summand. And so the same thing is going to happen here. So just like last time, the idea is to construct a decomposition R, F, push forward, QL as a direct sum of things. So I'm going to call them PI. Such that each PI is stable under the Hecke correspondence. And T acts by multiplication by minus I. In the ith factor. Now, I'm not going to tell you what this decomposition is because it's a little bit complicated. But what you get, hence, for all EA, for every one of our rank n-1 non-degenerate Hermitian vector bundles, we get a formula for the degree of the intersection of the naive cycle with this codimension R thing L. So I've already claimed that I've constructed this operator T in such a way that this is the trace of Frobenius composed with TR acting on the stalk of this sheaf. But if you believe that this sheaf has this decomposition such that T acts in this particular way, then you get something like an explicit formula, at least insofar as these sheaves PI are explicit. And then on the analytic side, one proves that, okay, on the analytic side, we've got this product of a Dirichlet function and some Fourier coefficient on the unitary group UN-1, but it came with a shift. But I don't want to put that here. That'll come later. Actually, I do want to put it here. Yeah. This should be the sum over I of the trace of Frobenius. So the left-hand side is some polynomial in q to the minus s. And these sheaves should be encoding the coefficients of that polynomial. And I forget where the shift is supposed to go. I think I messed that up. Where does it go? Here. No. No. Put it here. And then I think I just need a +1 here. Right. And then if you can do that, then you're done. So then you just apply the Rth derivative to get this expression up here, exactly as in the last lecture. But in order to construct this decomposition and understand how the Hecke operator acts on it, just like in the last lecture, you have to really have a detailed understanding of the geometry of this Hitchin vibration. And so I'm going to describe to you roughly what this Hitchin vibration looks like. So in the non-degenerate case, where this Hitchin space M was parametrizing isometric maps between vector bundles of the same rank, one of the key things was that the Hitchin vibration was generically finite at all. And here, it's not. So what does it look like in this situation? So here's what happens. So we can factor this map. Consider the factorization M going down not just to A, but inside we're going to have A cross bun U1, where bun U1 is the moduli space of self-dual permission line bundles. That's prime. And what is the map? Well, remember this M was classifying rank n-1 EA and rank n F and a map from E to F. So the map from M to A just remembered EA. How do I get a self-dual Hermitian line bundle? Well, I just take this self-dual rank n bundle F and I take its determinant bundle, and that'll have a Hermitian form on it, and I'll get a self-dual Hermitian line bundle. So the map is, let me write it like this. One of these guys maps to the pair E comma det F. Just remember that much of F. And okay, this map, understanding what this map is on the bottom and understanding its cohomology is the same as understanding the cohomology of bun U1. And I claim that somehow this map on top looks a lot more like the Hitchin vibration than we had last time. It's still not finite at all, but it's something that we can understand geometrically. So first, let me say this. I mean, we're trying to somehow, the first question is, how are we ever going to get a Dirichlet function appear in the geometry of the Hitchin vibration? It's in this bun U1. So fact, this Dirichlet function, in fact, is the alternating sum of the trace of Frobenius acting on the cohomology of bun U1. That's where the Dirichlet function appears. Then we've got this Eisenstein series that's supposed to appear. But we kind of saw last time how you're supposed to, they came from these density polynomials, and these density polynomials were related to the old Hitchin vibration. The Eisenstein series are going to come out of the cohomology of the fibers of this top map. And so what does this top map look like? So as in last time, there's some decomposition of A into some ADs. And there is open dense Each one had a regular semi-simple locus. And last time I showed how there was a finite Ital Galois cover of the regular semi-simple locus, whose Galois group was this semi-direct product of the symmetric group with d copies of plus or minus 1. This top map, so we've got M mapping down. So now let's just restrict to this open and closed part of A indexed by D. And let's pull it all the way back. So let's restrict to the regular semi-simple locus and then pull it back to this Galois cover. Right? So what you get is D copies of P1. It's a D-fold product of P1 bundles. So this is the explicit understanding of the Hitchin vibration that makes everything work. The point is that somehow in the old situation, this would have just been a finite Ital cover. And so the fibers of this map in the old situation would just be points. A D-fold product of P1 bundles is not a finite set of points, but cohomologically, it's not that different because the cohomology of P1, it looks like it's 2 points, except that one of the points somehow has a Tate twist on it from the degree 2 part of cohomology. And in the end, that Tate twist is the thing that accounts for this extra plus 1 that gives you the shift between S and S plus a half. And so this is what the Hitchin vibration looks like. And once you have this explicit description, somehow this decomposition and this analysis of the Hecke operator come from examining how the Hecke correspondence operates on these P1 bundles. And this is all very complicated, and I don't want to say anything more about it than this. Once you've got the geometry of the Hitchin vibration, you've got something concrete to work with. Okay? So more stuff happens. But I want to move on because there's something else that I want to tell you about. So the title of my lecture series involved L functions, and so far there have been no L functions. So let me spend my remaining time talking about the connections with L functions. All right. So everything comes through the doubling integral. So let's fix a D at least 1 and start with an unramified Siegel-Eisenstein series. EHS on U 2D, 2D. So we're taking N to be 2D now. You can take the diagonal restriction along UDD plus UDD into U 2D, 2D. So this, remember, is inside of GL4D. So you can just take the block diagonal inclusion. When you take this Eisenstein series and pull it back, you get the Dublin kernel. So you get some automorphic form in two variables. Where now my h is always going to be udd. So we've got an automorphic form in two variables on udd. So the doubling integral of various people, I think first Bocker, and then later Piatetsky-Shapiro, and Dallas, says the following. For an unramified automorphic form F living inside of some cuspidal irreducible automorphic representation, so inside the space of cusp forms on H, if I take this automorphic form on H, integrate it against the doubling kernel in one of the variables to get an automorphic form in the other variable, okay, so whatever this integral is, it's an automorphic form in the variable h1. What is it? It's the thing that you started with multiplied by an L function. The base change L function of this automorphic form, shifted by a half, f of h1. So now you could take this, you could integrate this form against another form. So this implies for all unramified f1 and f2 in pi, if I look at the double integral. So this is the way it's usually stated. It follows immediately from the previous formula that this is the same L function times the integral of f1 and f2 against each other, which is the Peterson inner product, the bilinear Peterson inner product. Okay, so here's two forms of the doubling integral, a strong form and a slightly weaker form. If I have an automorphic form in two variables on my unitary group, it has sort of a double Fourier expansion. You can take you can take Fourier coefficients in each variable. So D, H1, H2, S has double Fourier coefficients. So D, E1, A1, E2, A2, S, indexed by rank D permission vector bundles, pairs of them. And you can ask surely these coefficients are related to the coefficients of the Eisenstein series on U2D2D that gave rise to this doubling kernel. And here's the relation. D, E1, A1, E2, A2 of S is some sum of Fourier coefficients of the original Eisenstein series where you're running over rank 2D Hermitian vector bundles where the underlying vector bundle is fixed as the direct sum, and the Hermitian pairing looks like this, where the sum is over all Hermitian forms on E1 direct sum E2 that restrict to A1 on E1 and A2 on E2. But the Hermitian form, these summands aren't required, it's not required to be an orthogonal direct sum. So the stars here are representing all the possible ways that E1 and E2 might interact with one another under this pairing. And now the point is, the special cycles kind of behave in the same way. So for cycle classes, so I'm going to start dropping the brackets that I've been putting on cycle classes before. So if I take two special cycles in codimension RD on the moduli space of U2D Shtukas, you get this intersection formula. It's basically the same. It's a sum of the special zero cycles indexed by, you take E1 direct sum E2, and you endow it with all possible Hermitian pairings that are compatible with the Hermitian pairings on E1 and E2. And so if we knew the arithmetic Ziegel-Wave formula sort of for all of these coefficients, for all coefficients of this form, then we'd say that the arith derivative of this guy is equal to this guy term by term. So assuming arithmetic Ziegel-Wave, we get that the degree, if I take any two of these special cycles in middle codimension and intersect them, I'm going to get the arith derivative at s equals 0 of the corresponding double Fourier coefficient of the Dublin kernel. Assuming arithmetic Ziegel-Wave. And as long as we're making assumptions, let's assume also the modularity conjecture. There exists an automorphic form, ZR, on our unitary group, unramified, valued in the Chow group of U2D Shtukas, whose Fourier coefficients are the special cycles, whose EA coefficient is ZR EA for all E and A. Now, if you assume that such an automorphic form valued in the Chow group exists, what is this relation telling you about it? It's telling you that if I take this automorphic form valued in the Chow group and I evaluate it at one point, and then evaluate it at another point to get two middle dimensional cycles, and then intersect them, and then take the degree, it's telling me that the result as an automorphic form in two variables is the Rth derivative of the Dublin kernel. Because this relation up here says precisely that those two automorphic forms agree Fourier coefficient by Fourier coefficient. Okay. Now, I mean, again, assuming modularity conjecture and assuming arithmetic Ziegler, we've got some kind of clear connection between intersections of cycles and something that we know to be connected to L functions. So how do you actually extract some nice formula from this? So this modularity conjecture allows us to form. By the way, all of this means somehow the idea that you can use arithmetic Ziegler to connect to the Dublin kernel and then form arithmetic theta lifts. These ideas are all due to Steve Kudla. I mean, he sort of dreamed all of this up a very long time ago and said, what if we could do something? What if we could do something along these lines? So what would be an arithmetic theta lift? Given an unramified hospital automorphic form on H, so a scalar valued form, we could integrate it against this form valued in the Chow group to get a class in the Chow group. So its arithmetic theta lift, theta of f, would be the integral of this cusp form against this function valued in the Chow group to get a cycle class in middle codimension. Okay. And now what happens? Okay, so what happens if I do the following? I can compute the degree of, okay, you can do a couple of different things here. The most general thing you might want to do is take this one class in the Chow group and intersect it against this entire automorphic form valued in the Chow group. So intersect it against ZR in some variable H1 to get a number. What number do you get? Well, if you just insert this definition of the arithmetic theta lift, you get oops. You get the degree. Oh, why is it doing that? Stop doing that. Blue. You get the degree of this generating series evaluated at H1 times the integral of f in some other variable against the generating series in some other variable. And then you interchange the degree and the integral, and you get the integral of f of h2 times the degree of the generating series in one variable intersected with the generating series in the other variable. So there's an intersection here. But this is the doubling kernel, or its Rth derivative. And now you pull the derivative out of the integral, and the doubling integral tells you that this is, so now the Rth derivative of the base change L function at 1/2, because there was a shift in the, back in the doubling integral. Where did it go? Yeah, back here, s plus 1/2. So you get the Rth derivative at 1/2, the center of the functional equation, of the base change L function. And remember, this doubling kernel just, it gave you back the form that you started with, now in the variable h1. So you get this formula. This is an equality of scalar valued automorphic forms. And now, what you can do from this equality, so from the degree of ZR H1 so from this equality of automorphic forms, you could either take the Peterson inner product of both sides against some other unramified form in the same automorphic representation. And what you'll end up with is the degree of the intersection of the two theta lifts, the two arithmetic theta lifts. Is the derivative of the L function times the Peterson inner product of those two forms. Or, starting from this equality, you could extract a Fourier coefficient from both sides. Or take the EA Fourier coefficient on both sides. And when you take the EA Fourier coefficient on the left-hand side, you replace this by its own EA Fourier coefficient, which is one of our special cycles. And on the other side, you're just taking the Fourier coefficient of this F. And so that would give you a different formula. The degree of ZREA intersected with this arithmetic theta lift is the Rth derivative of the base change L function times the EA coefficient of the form that you put in. To make all of this work, so one, we don't know the modularity conjecture. Two, we don't know arithmetic Ziegelwey. for all EA. We only know it for the non-degenerate ones, and plus when the kernel of the Hermitian pairing has rank 1. We only know those cases. And 3, and I mentioned this at the end of the second lecture, degree is not well defined. Because this moduli space of Shtukas, U2D Shtukas, is not proper. As soon as D is greater than 0, actually, when 2D, as soon as 2D is greater than 1, so it's not proper for any D. Wow. So this one, the issue with the degree, I kind of explained how to get around last time. You can use Chow groups with proper support, but something somewhere that you're intersecting, you have to start with something that has proper support. And this, we don't know enough Ziegel-Weis. Well, you could ask, is there a case where the Ziegel-Weis formulas that we now know are enough to make this argument go through? And this modularity conjecture, well, at the moment, we're just kind of stuck with that. So here's the theorem, the final application. This 2 and 3 are disappointing. So, okay, here's the theorem. We can only get a theorem in the case where D equals 1. So our H is the group U11. And we still have to assume the modularity conjecture. Then Zhang on the existence of this generating series of cycles ZR. If pi is some unramified cuspidal automorphic representation of H, so let's say admits an unramified vector. F. Then, for all non-degenerate rank 1 Hermitian vector bundles, EA on X prime, if you take the corresponding middle codimension cycle and intersect it with this arithmetic theta lift of this unramified vector, you get the expected formula. You get the arth derivative of the base change L function times a factor that remembers exactly which unramified vector you chose. I mean, it's a one-dimensional space of choices, but you still have to remember it somehow, and exactly which cycle you put in here, and it's just the EA coefficient of the F that you put in. And this business about the degree not being well defined, well, I said at the end of the second lecture that in this situation, for these special cycles, the special cycle itself is proper. So since ZREA is proper, you can make sense of the degree because what we're actually intersecting is something in the codimension R Chow group with proper support. U2 Shtukas now, across the usual Chow group. But there's an intersection pairing between these into the Chow group of 0 cycles with proper support. And that has a degree on it. And that's the degree that's appearing here in this theorem. And finally, since I'm out of time, let me say that in the number field setting, okay, so we had two, where'd it go? Yeah, we had two possible applications. In the number field setting, this formula is known. This is the arithmetic Rallis inner product formula of Chow and Yifeng Liu. But in the number field setting, you're allowed to do certain things that don't make sense in the function field setting. Like whatever the precise statement is in the number field setting, it doesn't involve any integral models. And the statement of the theorem is something that's happening purely in the generic fiber using the valence and Bloch height pairing. And in the generic fiber, you can do a lot of tricks to add level structure. And also, if you think all the way back to the first lecture, the special cycles involved some extra parameter, some sort of Schwartz function that's somehow tied up with the level structure, and nothing like it ever appeared in the function field setting. And in the number field setting, they're allowed to play games like choose really high level structure that allows them to choose these Schwartz functions in such a way that when they start intersecting things, they never see any improper intersection. And because they never see any improper intersection, when they eventually use the arithmetic Ziegel-Weyl formula of Chow, Li, and Wei Zhang, they only need it for the non-degenerate case, for cycles indexed by non-singular matrices T. And these tricks that avoid the degenerate cases don't seem available in the function field setting, at least not in any obvious way. So in the function field setting, we're limited at the moment to just this one little case where d equals 1, and you get this by combining the two theorems that I've stated, the Feng, Yun, and Zhang arithmetic Ziegel-Weyl for non-degenerate coefficients, plus the new result for just the coefficients that are a little bit degenerate. You put those together and you get this result. And I'm out of time, so that's it. Thank you very much.
Doubts. The many integrals which came up in this lecture, are they finite sums or they are infinite sums? There were integrals all over the place.
Yes, yes. As long as I'm only integrating a cusp form, they are in fact finite. Yeah. Yeah.
They are finite sums?
I'm pretty sure. Let's see. Maybe not. Maybe not the one in the doubling integral. The one in the arithmetic theta lift, yes. The one that appears in the doubling integral, no, probably not.
I mean, there is a famous theorem of Harder.
Right, exactly.
Forms are
Right,
compactly supported.
right.
But I was
So
a bit confused. Your cusp forms are complex valued or they are FP valued?
they're complex valued.
But then when you do integrate and you want to get into the Chow group, is the
Yeah.
Chow group FP valued or complex valued?
Complex valued.
But if we are looking at function field of a curve, the Chow group is it's a vector space over C.
Yeah, it's a complex vector space. Yeah.
But I mean, one would think of Chow groups as some kind of Jacobian, etc., or cycles.
Well, I mean, it's really, I mean, except for some stacky issues, it really starts out life as just an abelian group. I mean, it's the abelian group of cycles modulo rational equivalence. for kind of stacky reasons, you want to allow cycles with Q coefficients. So really the Chow group starts out as a Q vector space, and then I've implicitly tensored it with C everywhere.
Okay. But then when you are integrating things with values in the Chow group and it's an infinite integral, is that making sense?
Yeah, I mean, because of Harder's theorem, because I'm only integrating against a cusp form. So as you say, by Harder's theorem, it is going to be a finite sum. Yeah. Yeah. The theta integral is fine, but I think you're right. For the same reason that I guess the doubling integral in this case is also going to be a finite sum.
But your objects themselves are non-compact. The HAF upon HF is a non-compact object.
That's correct. Yeah.
And you are doing
I mean, we're integrating over a non-compact space and getting values in some possibly infinite dimensional complex vector space, but it's
the Chow group.
Yeah, the Chow group. Yeah, but it's the compact supportedness of the cusp form, Harder's theorem, like you say, that makes this all okay. Yeah.
And these theta functions that come up, are they usual theta functions which appear in Weyl? You know, the theta that you have, are they the usual theta functions, or there is something else called arithmetic theta functions?
When you take zero legs, where did it go? This right. Using arithmetic equal V, assume the modularity. Right. When you take zero legs, this is essentially a classical theta function. I mean, it's going to be valued in some, it's how to say this? I mean, it's not quite, because this space is not going to be one-dimensional. Let's see, what does it look like when you take zero legs? So now we're just taking zero cycles on a discrete space. Right. So, okay. So think about it this way. Imagine that R equals 0, okay? Then I'm looking at zero cycles. This whole thing just becomes 0 cycles on rank 2D self-dual vector bundles. So let's see. What do? You would fix one of these things, F, and this space of Shtukas, when R is 0, is going to be highly disconnected. So this F is actually picking out, it's the point that this F is actually a connected component of this. And so in the Chow group of this horribly disconnected thing that's just points, I can just sort of project onto that one connected component. And that'll give me a one-dimensional vector space. So I'm saying that F determines some copy of C sitting inside of here as a direct summand. And then I can project onto that direct summand. And then this function would become the classical theta series associated to this vector bundle F. Does that make sense?
Yeah, perhaps. So, okay. So eventually these theta functions are classical theta functions. But
when there's zero legs, yeah.
But I'm not sure whether the Ziegel-Weyl formula developed by Kudla and Rales has also been developed in the function field context. You know, Kudla and Rales wrote many long papers about Ziegel-Weyl.
Yeah, the regularized versions, yeah.
You use the regularized versions, or you use only the versions where things converge?
So it doesn't use, oh, okay. There's two ways to interpret your question. One is which version of the Ziegel-Weyl theorem is going into this proof? And the answer is none, ever. In Feng Yunin Zhang and in this also slightly degenerate case, it's just giving a new proof of what the Ziegel-Weyl theorem should say, but only for specific coefficients in the equality. the other way to interpret your question is, okay, if this is giving some new proof of Ziegel-Wey in some cases, matching up to some coefficients, not the entire equality of automorphic forms, are those, where do those, I mean, in the Kudla and Rallis papers, there's various cases where they have to regularize things in increasingly difficult fashions. And you could ask, in this version that's being proved, where in that spectrum of regularized versions does this lie? And I don't know the answer. I have not sat down and thought about that.
Right now, I think it's getting a bit late, so I will.
Okay.
So you don't refer to Kudla-Rallis?
No, no. This is in fact a new proof of some instances of the Ziegel-Wey formula. Yeah, that's right.
But it's about the similar theorems in the function field.
Yeah, I mean it really is reproving some versions of the Ziegel-Wey formula using a totally different argument than anything that's in Kudla-Rallis. Yeah.
All right. Thank you.
You have a question? Yeah, I have a question. So if my memory serves me right, yesterday when you did this projection, there was no churn class coming up in the non-degenerate.
Right.
So
correct.
what is the subtlety in the first churn class showing up here?
Oh, it's because it's in, because it's in the statement of the theorem. I mean, it's just sitting right here. In the one yesterday, we started with
okay. So
there was
all
a
right.
zero
Okay.
cycle, and we were counting points on the zero cycle.
So you have that even in the statement of the theorem, and that's why
Yeah.
it shows. Okay.
Built into the statement, and so it's got to show up somewhere in the proof.
All right.
Yeah,
Okay.
that's it. Yeah.
Okay. So if there are no other questions or comments, let's thank Ben for his wonderful series of lectures. Thank you, Ben.
Thank you. Thank you very much.